Okay, to continue, let's look at an application of the harmonic oscillator potential. Okay, 1 second. There we are. So we've been talking already. We found out that for the harmonic oscillator potential, we have equally spaced energy levels, which is kind of neat. So the energy of the lowest state is 1/2 h bar omega. The next one is 3/2 h bar omega, 5/2 h bar omega, and so on. The spacing between any two of them is just h bar omega. This is what the wave functions look like. And then this is a sketch of the probability density for each of these states. Notice that rather like the finite well, the wave functions penetrate into the forbidden region. They penetrate outside, beyond the point where the potential energy starts to exceed the energy of the state. Okay? All right. Now, let's look at an application. So here's the thing. Many physical systems have a potential energy as a function of position that has some potential minimum in it, okay? And the idea is that near that minimum, the potential energy will probably approximate a parabola. And so in the vicinity of that minimum, okay, near the ground state, the system will probably look like a harmonic oscillator. So one good example is the interatomic potential in a diatomic molecule, okay, which is sketched here. So the exact potential might look like this black line. This is the potential energy as a function of separation between the atoms in the diatomic molecule. Here they share a covalent bond, okay? By the way, the 0 in this diagram refers to the energy of the two atoms when they're widely separated. Okay, so that's the exact potential. The blue dashed line is a harmonic approximation. And you notice that in the vicinity of the potential minimum, the harmonic approximation is very good. So we might assume that at least for relatively low vibrational energies, the predictions of a harmonic model will be pretty accurate, okay? So, and what are those predictions? Well, the main one is that we should get equally spaced energy levels. Here, let's look at an actual example. Here's a vibronic spectra of boron difluoride of a molecule, okay? Vibronic means that we're looking at transitions between vibrational states. Actually, in the data that's shown here, the molecule goes from its ground state to some excited electronic state, but we can also be left in any one of the vibrational states associated with the excited state, okay? So that means that starting from here, this is the transition from the lowest, from the initial state to the lowest vibrational state of the upper manifold. So that's this one. And the next transition is the state to the quantum number equals 1 state, quantum number equals 2, 3, 4, 5, 6, and so on. And you'll notice that these states, these lines, are all approximately equally spaced, indicating that the harmonic model is a very good model for at least for these states in this molecule. So the vibrational states of molecules approximate harmonic oscillators, and so their quantum states are nearly equally spaced. Pretty cool. You'll do the last lab that you'll do will look at a system like this, another diatomic molecule, and you'll look at the vibronic transitions like this. Okay. Here, let's do a simple example. 1 second. Let's look at the vibrational mode or vibrational absorption of a diatomic molecule. Let's say HCl. Okay? So in HCl, of course, we have a heavy chlorine atom and a light hydrogen atom, and they're bound together somehow. Okay? And in the harmonic approximation, we assume that the bond between the atoms can be treated as a spring, okay? That has some spring constant. And it seems like a silly model, but actually it works really well, as we just discussed, okay? In order to look at this more quantitatively, we can go one more step and cast this problem into center of mass coordinates. In the center of mass frame, it's as if the hydrogen atom were attached to a unmoving point by a spring, only the mass of the hydrogen atom should be replaced by a reduced mass, mu, where mu is equal to the mass of the hydrogen times the mass of the chlorine divided by mass of the hydrogen plus the mass of the chlorine. So for example, the mass of the hydrogen is about 1 atomic unit, the mass of the chlorine is about 35 atomic units, and then we divide this by 1 plus 35 atomic units to get approximately 0.97 atomic units. Okay, not so bad. Now let's take a look. If we look at an infrared absorption spectrum of HCl, we find that the main absorption line occurs at a frequency of 8.66 times 10 to the 13 hertz. And this is a frequency in the infrared, something you can measure with an infrared spectrometer, okay? And just to be clear, what we're seeing is the following. The interatomic potential between the atoms looks something like that. And the energy states of this potential are approximately, actually quite close to, the energy states of a quantum harmonic oscillator. And what we're looking at is this transition from n equals 0 to n equals 1. And the energy of that transition is just the energy difference between the n equals 1 state and n equals 0 state. And as we've already discussed, this difference is just h bar omega naught. Okay? So since we can measure this frequency, we can determine everything we need to know. So for example, we might want to know the spring constant of the molecule. How strong or how springy, how stiff is the bond between the atoms? So in the harmonic approximation, the bond stiffness is characterized by a spring constant. And of course, the spring constant, K, is equal to m omega naught squared. And now you can put in numbers and find this value, because m is 0.97 times the atomic mass unit, about 1.66 times 10 to the minus 27 kilograms. And omega is 2 pi times the frequency that we just mentioned, 8.66 times 10 to the 13, and then squared. And evaluating this gives the following: 477 newtons per meter. Of course, it's kind of funny to talk about the spring constant of a molecule, and it's funny to give it in units of newtons per meter, because you can't stretch the bond by 1 meter. That would be ridiculous. If you stretch it even by an angstrom, you you'd leave the harmonic region and actually break the bond between the atoms. But for very small perturbations around the equilibrium length, this spring constant describes the dynamics. Okay? Okay. One of the interesting things about these types of measurements is that we can kind of verify what we're doing by doing isotopic substitution. So suppose that we replace the HCl by DCl, where D here is the deuterium. It's just a heavy isotope of hydrogen that has both a proton and a neutron in the nucleus. So it has the same chemical properties as hydrogen, but it has twice the mass. Okay? Now, since it has the same chemical properties, we would expect that for this molecule, K would be unchanged. But the mass changes, so that should change the frequency of the absorption line. So see if you can figure out what the frequency of the absorption line should be for this molecule based on what we already know. And I'll bring the reading question up in one moment.